Hi everyone, my name is Anna and we're here with Science at Home with Armagh Observatory and Planetarium. Today I'm going to be talking very briefly with Gavin Ramsey. Hi Gavin.
Hello there. Hi.
About a video one of his colleagues, Mark Garlick, has created, which will be shown at the end of this interview. So hopefully you'll get a wee bit of context for that video. All right, Gavin. Hi there.
Hi.
So how do you know the creator of this video? So the creator is Mark Garlick, YouTuber.
Well, so me and Mark did our PhDs a long time ago in the same place, the Mullard Space Science Lab, which is part of UCL. And so this was in the early 90s, so a long time ago. And we were both using data from a new X-ray satellite called ROSA. And this was the very first survey of the sky in soft X-rays. And it was picking up very new and exciting binaries of the sorts that we were both looking at. Now, Mark looked at those systems called intermediate polars, which you'll find out what they are in his video. And then I was looking at polars using ROSAT. And this was an exciting time for cataclysmic variables because many more systems were being discovered by this new instrument called ROSAT. And it kind of just demonstrated what happens to science areas when you get a new piece of kit. In this case, it was a new exciting satellite, and we were discovering lots of new sources. And then so Mark did, I think he did one postdoc, but then he went in to do space art. And then, so I would encourage everyone to do a search on Mark Garlick, kind of artist, astronomer, and he's got a whole bunch of fantastic kind of images of different types of astronomical sources. So do check it out. And this is what he's been doing for some considerable time. I'm afraid I've not been doing anything quite as exciting as that.
Well, they went in quite different directions then in the end for having done the same.
We did.
Yeah. Okay, is there anything else you'd like to say to introduce this video?
Well, so what you'll find is that kind of Mark, in the video, he shows different sorts of binaries, ranging from the ones I've mentioned, but he finishes on two merging neutron stars, which are at one end of the extreme scale of binaries. So you have two neutron stars, they're maybe several times the mass of the sun, but they're orbiting, they both have the same size as Loch Ness. Okay, so kind of Einstein predicted you would get two neutron stars, and they would eventually merge, and they would emit lots of gravitational radiation. This is what Mark's final choice of binaries are. And so we're involved, Armagh is involved with a project called GoTo, and this is looking for the optical counterpart of these merging sources, which LIGO and Virgo have been identified. Now, although GoTo, which is located on La Palma, although it's a robotic telescope, all the telescopes in La Palma are currently closed, whether they're robotic or not. And that's even so, if a robotic telescope, it should be able to do its thing all by itself, and normally everything goes fine. But if there was one night when something went wrong, say the observatory dome, say it couldn't close and there was no one there to assist, this could be very bad. So all telescopes are currently closed on the Palm. But we're involved with this mission called GoTo to try and identify the optical counterpart of these merging neutron star binaries.
Brilliant. So even though we went in different directions, it's all come back to
strange. Similar. And it shows that people doing degrees in astronomy and astrophysics, sometimes they can take very different routes to what people are doing now.
Yeah, absolutely. Okay, so what is a white dwarf star?
Good question. So these cataclysmic variables, they're a binary system. So you've got a white dwarf orbiting around a low mass star. So in this case, a white dwarf is basically, it's the end state of most stars. So our sun in whenever 3 or 4 billion years time will expand to be a red giant, and then it will puff away all its outer envelope, and it will create something like a planetary nebula, which you might people might have seen, say the Ring Nebula, which you can see with small telescopes. It's like a little ring, and what is left of the star is what's called a white dwarf. So a white dwarf is maybe half the mass of the sun, something like that, but it's squeezed into the volume of the Earth. So they're dense remnants of stars, and they'll cool down forever until you're left with something which is essentially not very hot.
Okay. And then because they're so dense, then they have high gravity. Does that affect?
Yes, exactly. Yes. And so in these cataclysmic variables, you've got a white dwarf and it's orbiting around a low mass star, and they are orbiting every hour or two, within an hour and 3 4 hours. So they're very close. So you
Okay.
can fit them into the size of the sun. And because they're so close, material is actually flowing from the red dwarf, the low mass star, on to the white dwarf.
Okay. And
And
then
in these cases, it creates an accretion disk around the white dwarf. But in the stars, which me and Mark were looking at, the white dwarf has a very strong magnetic field, which actually prevented the formation of an accretion disk. And so you get lots of exciting, quite extreme physics where the material flows onto the magnetic field lines of the white dwarf and gets dumped onto the white dwarf, which generates lots of X-rays.
Okay. And then does that emit gravitational waves?
Well, at the extreme case of these so you also get white dwarf binaries,
Okay.
which are orbiting around each other. The most compact binary system which we know currently is called Canker. And many years ago, we found the optical counterpart of this X-ray source, and it has an orbital period of 321 seconds, which is just over 5 minutes.
Yeah.
Now, we've probably been speaking for about maybe 5 minutes. In that time scale, both of these white dwarfs will have orbited around once in these binaries. And so they are predicted to emit lots of gravitational radiation. And so there's a mission called LISA, which is a European Space Agency mission, which may be launched in 10 or 15 years' time, and it's in space, and it's trying to find gravitational waves. And the very first sources which it will pick up are these white dwarf binaries.
So what do gravitational waves mean then? We all heard about the discovery of them and things like that, but maybe not so sure what they are.
So just think about it. They're essentially ripples in space.
Okay.
So if you can imagine, say, a trampoline, and you bounce on the trampoline, you're creating a deflection in the trampoline, but you can think of it as space being curved. And as you get merging objects, say neutron stars, they emit lots of gravitational radiation, and ripples extend throughout the universe. And if you've got very sensitive measuring devices, which they have in LIGO, and the thing to remember is people spent 50 years building detectors like LIGO to try and measure the minute, absolutely minute differences between 2 points as gravitational radiation sweeps by. And so when they detected the direct detection of gravitational radiation in September 2017, I think it was, this was, in my view, one of the greatest discoveries of science because it was so spectacularly difficult to do.
Yeah. Okay.
The problem is, when these gravitational wave detectors find a new event, sometimes it's generally not very clear in the sky where exactly they were. So normally it can be anywhere within quite a large patch of sky. But if they're neutron star mergers, you would expect them to be detected in optical light just after the gravitational wave were released. And if you can detect that, you can then get many more different kinds of observations at optical light and X-rays to try and find out more about it. And this is what happened 2 years ago. I'm afraid I forget the dates, when they actually found this event in gravitational waves, and then I think 12 hours later, 15 hours later, they found a new object in a galaxy which was just at the right distance, which was the optical counterpart. And this became one of the most studied, best studied astronomical events ever.
Brilliant.
So that was very exciting.
It's really exciting stuff.
What we're doing with GoTo is we're trying to identify the optical counterpart of the next neutron star mergers.
Brilliant. That was really interesting.
It's great stuff. It's very exciting.
You seem like you enjoy it a lot, so that's great. You enjoy what you're doing.
Absolutely, yeah.
Yeah. All right. Well, I think we'll leave it there. So thank you very much, Gavin, for having this wee chat with us.
My pleasure.
I'll see you again on Science at Home, and I hope you enjoy the following video. It's really beautiful. Okay, bye.
Okay, bye.